I will be talking a little bit about spectral analysis and time frequency analysis. So let's dive in. There was a little bit of wish list of topic that we should cover to prepare you for the hands-on. So I made a little bit of sections, how to compute stuff, how to interpret stuff, and my examples are drawn from EEG, MEG, and intracranial data. So let's check. So a general problem in science is that we have often interesting data and we want to detect systematic patterns in the data. And I think many of you are familiar with doing some kind of statistical modeling with data. So one approach is to express data as a linear combination of several factors. So for instance, if you look at this example data that has nothing to do with EEG, it's airline passengers per year. Maybe you can think that this data would be modeled quite well by a linear factor, linear growth pattern, and something that is cyclical. So the approach would be we find the optimal weighting, the coefficients for examining our data in that way. So let's see. We do perform a model fit. I mean, many of you are probably familiar with fitting these very simple models, and we achieve a quite good fit. So in that way, we can describe the data in an efficient way and maybe explain the data to some part if we find interpretation for the factors. So I mean, the cyclical part would be the yearly change. Okay, easy. So let's see if we can apply this procedure to our very small snippet of EEG data. So this is 1 second of EEG data. It's 500 data points. And I mean, you notice that there's something cyclical going on. So maybe a good idea would be to fit some kind of sine. And I eyeballed it and I fit a sine with a fixed frequency. I noticed that this fit is not great. So I need a little bit more degrees of freedom to fit the cyclical pattern. So let's see. To get this degree of freedom, I can use a complex sine, so which is a sine and a cosine added together. So you notice that I achieve a much better fit of my data with one complex sine of a fixed frequency. All right, so let's see. Okay, this model worked quite well, so let's just try to do it for a little bit more data. So here it's now 2 seconds of EEG data. We fit the model, we find the perfect coefficient which matches the data the best, and it doesn't work so well. Sad. So maybe we don't have enough factors. So let's try to do it with even more sines. So I pick, and maybe my eyeballing of the frequency was not perfect. So I now do it, I put in more factors. I put more complex sine in with different kinds of frequencies. And you see that some features of the data are matched quite well, like this little changes in amplitude, but others don't. Okay, but maybe it's a good direction. I add even more factors. Let's see. Oh, wow, I achieved a perfect fit. My model is perfect just by using a lot of factors, a lot of complex sines. Okay, is that a good approach to dealing with things? So what I did was to take my time series with some samples and use a lot of sines with specific coefficients to fit to the data. So I asked my statistician friend, my favorite statistician, and she will say, yeah, it's okay. You fitted a multivariate linear model with complex sinusoids as regressors. But Natalie, it's a little bit strange. Your model has 0 degrees of freedom. You don't have any remaining residuals. You're completely overfitting the data. Okay, that's one view. And I go to my signal processing friend, and she will tell me I just did the Fourier transform. I transformed the data from the time domain to the spectral domain. And this is a very standard thing, and I was able to represent the signal in a good way, and there's no information lost. I can completely recover the signal just using these coefficients. All right. So this is like a technique that is often used to examine EEG data, and I think by framing it in terms of statistical modeling, many people understand what's happening. Maybe. Let me know. Now we approach this overfitting issue. Can we kind of like improve so that our coefficients will be kind of like general? And what we would use, for instance, is a method that uses averaging to generalize the coefficient. So let's see how it works. Very simple. So you take your EEG or MEG data and snip it into little segments, segment 1, segment 2, segment 3, and so on. You multiply it with a windowing function, a taper, which which modifies the data a little bit in terms that the edges are a little bit different. More about that later. And then for each segment, we compute the corresponding spectrum, the coefficients that best model the data in terms of sinusoids. What we can then do is average these spectra for each segment, and we have more of them. And we can plot a very common representation in MEG-EG research, which is a spectrum. So here is the average spectrum in dark blue. And you can see that's definitely some variation around the average. All right, so this is one of the main outputs of of spectral analysis. So let's check what we can do with it. So the main thing that we are doing is to plot the coefficients. And what we are doing is we plot kind of like the combination of the cosine and sine together so that we get a value for each frequency. And there are different ways to plot them, and it emphasizes different features of the spectrum. So we can plot the frequencies in a linear manner and the coefficients in a linear manner. We will see like a spectral peak here, but maybe some details are lost. So to emphasize them a little bit, people often plot the y-axis in log scale. And often you would also plot the frequencies in log scale. So, but this plots contain the absolute same information. It's just emphasizing different aspects. All right. When estimating these spectra, we have some parameters that we can look at. So these are how long these little data segments are, how many points we take, how many there are. I don't know if you noticed, but here there's a little bit of overlap between the segments. So some of the information is shared. across these different segments. And we can adjust the windowing function. So let's check a little bit more in detail what is this. In general, and if you are starting out, you're often asking, okay, it's a lot of stuff. What is the correct way to do it? And sadly, I cannot give you the answer, this is the way, because it definitely depends on what you want to achieve. But I mean, many people have thought about it before, so often there's like stuff you can draw from previous literature, but at some point you should build some intuition what these parameters are about. And you can use, for instance, simulation to achieve that. All right, so let's, for instance, check the segment length. So how long should this little segments be to which you are using for computation of the spectra? So the thing is, if you use quite long segments, you will achieve a specific frequency resolution. So a whole period of the oscillation has to fit into the segment for it to be resolved. So for instance, if you have a very short segment that's only 100 milliseconds long, you cannot really estimate the coefficient for a 1 Hertz sine. So the minimum we can do is, 10 cycles. Fit, like you get a 1, if your frequency is 10 Hertz, in here there will be 1 cycle of the 10 Hertz oscillation. So let's check this in on a real example. Okay, so here I cut my signal into 4,000 segments, and each segment is 100 samples long. If I just give that to my favorite toolbox, this is the output I would achieve. So I would not get an estimate for these frequencies typically. I would get an estimate for 10 Hertz, because that's my minimum resolution that I can achieve here with this very short segments. Right, so one way would be to increase my frequency resolution by making the segments longer. So here I have more samples per segment, so I can also get an estimate of the lower frequencies. All right, so and as I increase the number of samples per segment, I can estimate more and more frequencies. At some point, you will get the problem again that you are not averaging out specific, you're not averaging over enough segments to generalize. So here you have basically the original procedure, the Fourier transform in its pure form. But you cannot see anything there. So you have to get some middle ground eventually. But it really depends on what aspects you want to look at. All right. So then this mysterious taper or windowing functions, what are they doing? So very easy. You just use them to multiply with your signal. They will smooth out the edges here. And that has a certain effect when estimating the spectrum. So this is a standard window. It will always attenuate if you multiply such a function with your time series, it will just decrease stuff at the edges, the values. And you can see how it looks like in the spectrum if you just have like a very simple sine function. So if I use the taper, if I use something like a specific window function, I can attenuate spectral leakage. That means I can reduce the amount of influence of these edge effects, so to say. So they are often used for making the spectral estimation more robust against that. There's also something that's called multi-taper, where you use different kinds of tapers for the same segment and basically average over all of these tapers. Again, with the intention to reduce noise or uncertainty in the estimation. So I used sine functions because they have very nice properties for fitting the data, but you could use anything, right? It's just a way to represent the data. Sine functions have very good properties, but it doesn't necessarily mean that in the brain there's I don't know, 500 sinusoids swinging up and down. It's just a way to represent data. So you have a convenient representation of the data, but you have not explained the data at this point in time. I mean, my data is fit almost perfectly. I can fit it even better than here. But you would not necessarily say that there are 500 triangle function oscillating in the brain. Right. So these are the very basics of spectral analysis, but the most important things maybe. So let's really dive in and check what we can get out of this for learning about the brain. So if you compute spectra for instance, different participants, so these are, I don't know, 200 participants, you will notice that the outcome that you get is very variable. So if you have heard about alpha oscillations, in some participants they are super pronounced, while in others they are completely absent. So you have nothing at 10 hertz that is raised, that is pronounced. And from this empirical observation, the community has made a specific vocabulary to talk about what you see in spectra. And these are based on Greek terms. People often divide spectra into canonical frequency bands. So delta activity, theta activity, alpha activity, beta activity, and it continues. And I think often the underlying notion is that one measure that we have, for instance, the alpha frequency, the alpha power, captures a neurophysiological phenomenon. But I think a good way, like something that you have to keep in mind is that this is a little window that determines our access to this neurophysiological entities, and it doesn't have to match perfectly onto what we want to capture. Just a few examples to illustrate that point. So for instance, this is the these are many participants, children that were measured very young and during development. And what you can do is you check the frequency of the rhythm that is most pronounced, which is the posterior dominant rhythm. And you can see that the frequency of this rhythm changes across development. So it emerges at 4 hertz, and then it approaches this canonical 10 hertz that is very common in adults. If you would now use the terminology on the last slide, sometimes you get a little bit of mismatch how people talk about things. So would you call this the theta rhythm? Would you call this the alpha rhythm? Just because it's like not matched by these specific frequency bands that people adhere to. And there's a little bit of confusion in terminology when talking about these matters. So this is something to keep in mind, maybe. Right, so there's a phenomenon, posterior dominant rhythm, and you use different measures to access it. We can compute things from our EEG data with Toolbox super conveniently, but we have to really make sure that we are measuring what we intend to measure. Different example, also from infants or children. So this is EEG activity of an infant, and this is adult EEG activity. And you can see that while in the adult, you see this prominent alpha bursts, basically. It's absent in the infant. The brain activity looks completely different. If you compute now the spectrum, you would see that you have a nice spectral peak for the adult. But for the infant, you also have something. So what is that something? But it's kind of like different in nature than what you have for the adult. So this is a very common ingredient of electrophysiological data. It's this 1/f type of activity. I think you see it in every data set. So here the power scales with frequency. So for low frequencies, we have the highest power, and it gradually falls off. And it can fall off with different exponents. So how fast it can decay. So I mean, people have regarded this activity as noise for a long, long time, but maybe it can also be measure something useful. So I think that is what we are figuring out at this moment. All right. But there's a lot of, I mean, the conceptualization is sometimes not clear. Are these measures that we compute? I mean, we can easily compute a spectrum and average in a specific frequency band. It's 2 lines in every toolbox, I guess. But what does it actually capture? Are you really intending to capture rhythm, an oscillatory type of activity at each time? Are you kind of like capturing a mixture of that? Do you have rhythms at every occasion, at every instance in time, in every participant, in every region? So I think when you're doing spectral analysis, you really have to think about this eventually. And there's also different types of measures that you can come up with. So maybe one approach is to not just average, I mean, basically average under this line, which is what you get, by just averaging the spectral values. Maybe you need to subtract something that you don't want if you don't want it. So we can come up with measures that actually intend to capture more specific things. Maybe it's not perfect. Maybe we need you to figure it out. Let's see. Right. Okay, let's skip that. Because in general, a spectrum is a summary measure. It's like a mean. Because in all the previous slides, I basically averaged across time. But across time, many things could happen. And your signal could look like this with really no visible, discernible oscillatory activity. So there's nothing on the single tri-level, which results in like a simple fall off 1/f type of spectrum. Or you could have changing dynamics that are visible as oscillatory bursts in a single trials, but then average out. So for this, we have to check a little bit more in depth. So what else here? So what we have in spectra is a little bit of a, I don't know, cone shape type dynamic where there's not a single, like a singular frequency that is showing this peak, but there's a gradual fall off. And this couldn't be related to the amplitude modulation of oscillator activity. So you see that the little troughs of the signal follow also gradual change, like the previous trough and the next trough are kind of like correlated to values. So let's demonstrate this a little bit. So if you have a sine function and you compute the spectrum of that, it gives you one singular peak at one value. If you have some kind of slow modulation going on and you modulate your simple sine with this modulator function, you will capture aspects of the modulating function in the product, so to say. So if you have changes in the modulating function, it will change the profile here. I made the modulating function here a little bit weird looking just to illustrate. But this is one factor that influences the width of the spectral peak. And there are many types of dependencies across frequencies. So you have to keep that in mind a little bit. So let's talk a little bit about higher frequencies. It can also be an example of dependencies across frequencies. So we often also find kind of like peaks in, for instance, the beta band, while there is also a strong peak in the alpha band present. So let's think about it, what it actually means. Does it mean that there is a rhythm that's oscillating at a faster frequency? From this plot alone, we cannot tell. So let's think about the physiology that generates that. So here I have a perfect sine with a little bit of noise on top, and it will give me a singular peak in the alpha frequency. If I have a signal that deviates just a little bit from the perfect sine, it will also generate so-called harmonics, peaks in higher frequency bands. And as there's more and more deviation from this perfect sine, the harmonics will become more pronounced. So I think we had the question in the tutorial, why do we have line noise at 50 Hertz, 100 Hertz, 150 noise? It's a similar thing. So I think I just want to say that while these entities look like nicely distinct, so there's an alpha peak and there's a very visually distinct beta peak, it may actually come back to the same neurophysiological entity. All right. So many things you have to keep in mind. So this is just for beauty, to show you that this is an actual thing that happens in the real brains. So here you see a nice rhythm that's recorded over the sensory motor region, and it has these very distinct arc-shaped form oscillations. So these will definitely generate also peaks in the beta band, and um, even higher harmonics. So again, it's a little bit faint, but again, you have a measure that you can define and easily compute, but you don't know what scenario, what underlying scenario you are capturing, and you have to think about what is really happening on the neurophysiological level. So are these distinct rhythms? Is it a singular rhythm with unusual shape? Or is it like both things at the same time? Because it's the brain and it's very complex. It's always the most complex version in my experience. So just to keep in mind some neurophysiological background. So we mainly plotted the coefficients of sine and cosine together to get the spectrum. But there's one type of information that is not really captured by this type of plot, just to keep it in the background. Is it playing? So you can actually change. So you can actually change the waveform, and you will retain the same spectrum because the relation of different how this frequency at 20 hertz relates to this frequency is not really visualized in this spectrum. So there's something that's called phase, which we don't really look at in this representation. But you can also extract it and examine it. It will appear in a bit more. Okay, so we already noticed that we have some kind of limitations if we average over time. Maybe this is not the right variable to average over, especially if you're interested in dynamic processes. So you often have the situation where there's something going on and you, I don't know, do something very simple, like open your eyes, see a stimulus, press a button, the dynamics will change, and we really want to investigate this. So for this, we need more information about time, and we compute something that's called time frequency representation. And it's very simple. It's the same plot as before. Cut the little segments, multiply with window function, compute the spectrum, but then don't average, but take these little spectra, rotate them, so frequencies on the y-axis, put some color on, ta-da. So very easy. I mean, for this signal, nothing super dramatic happens, but you can see that this 10 hertz oscillation is not always super pronounced. So there's some variation in the amplitude. All right, but this is just very easy to get in a sense. Okay. More complex dynamics than in my example on the previous slide. For instance, this is an example from also the sensory motor cortex, best cortex. So here you have some kind of movement going on in this period. It's I don't know, flicking your index finger basically. And you can see that it has different dynamics in alpha band, beta band, and often we use some kind of baseline to compare the dynamics to. So here we have a decrease in beta band activity compared to the baseline, and here we have an increase again. And I think we will play a lot with baseline in the next tutorial. So I think that then it's most easy to understand. Right, and again, you also have parameters that will influence how this representation looks like. So this is time, frequency, and you have mainly the parameters that influence how much information you take into account when computing like a single point here. Do you use long segments to compute your estimates? Then your neighboring values over time will be very correlated. If you use only short windows, then neighboring values will be more independent from each other. But little window, Adrian. So there are parameters that influence how your time frequency representation looks like. It really depends on what you want to achieve with this. So it depends on your research question, what would be the best way to do it. So you can use a fixed window length for each frequency, or you can also adapt the information you want to account per frequency. So maybe it makes sense to take a longer window for the slow frequencies because you need more information, like more cycles to capture them more. You need more samples, so it actually contains the same cycles as the later frequencies. So there's a lot of adaptation you can do. Okay, I'm too slow. So, but maybe let's check a little bit about this phase information that I talked previously. So, I mean, here's a little bit visualized. We have several trials, and we have the activity of them over trials. And here it's like a perfect sine activity. And now you can check how aligned they are over trials. And this is called intertrial coherence, intertrial phase coherence. And if they are super aligned, then this value will be very high. So if we look at it at the time 0, and we check the phase at each time point, it will be very, very similar. But as trials become, I just have to close the window again. Warning, warning. No, okay. Oh. Okay, sorry. So as we put the trials out of alignment, this intertrial coherence gets smaller in a sense. So this is some concept to take away. I think there's, for M&E, there's definitely some examples of that in the tutorials. For the other toolbox, I think also. So let's skip a little bit. Right, so it really depends if you have like a shift in alignment, for instance, across trials. It really depends where you average, if you want to compute, for instance, the power. Do you want to compute them for the single trials and then average them? or do you want to compute them on the averaged ERPs, which is also possible. If your trials are super aligned in activity, this will be very similar if you, for instance, compute the power, but sometimes the activity can also average out, basically. So this is called evoked activity, and this is called induced activity because there's no such strict alignment of the activity, if you ever stumble across these terms. So, and again, it's a little bit terminology. If you compute the power of such an ERP, it will give you power in these kind of like frequency bands. Is this now an oscillation? Is a single cycle enough for having an oscillation? Not sure. You really have to, I mean, this plot alone is not telling you something about neurophysiological origins of your activity. So by interpretation, you have to think about what this blob of activity will represent. So right. So after computation, the work is not done yet, sadly. So this is a little section just as an outlook to what we will do tomorrow. So far I only talked about spectra of single channels mostly, but I mean, you all know that we have more channels. So if you compute the spectra for all the channels in your EEG experiment, you will notice that they are often very similar, but also distinct. So let's examine that a little bit. So the main takeaway here is that channels are not independent measurements. Right, so if we think about how signals come about. So for instance, here I did a little simulation. I placed an active source in the somatosensory cortex. Oh yeah, it's still, I mean, you can watch the pattern, relaxing. And I varied the orientation of the signal generator. And with some modeling information about the geometry of the brain, how it looks like, and where the sensors are located. So this is EEG now. You can calculate how an active source that has this location and this orientation would contribute to the activity of sensors here. So, and you notice the pattern is kind of smooth and it's far-reaching. So if you have activity like here, you will also notice it in channels that are over here, basically in the visual cortex a little bit, like with much smaller contribution, but there's definitely contribution. Right, and I mean, for some orientations, you mostly have like positive contributions, so only red. And for other orientations, you have like basically a sign flip between neighboring channels. So, of course, not only one source will be active in the brain. So here are some examples of oscillatory sources, all with their distinct spectra and distinct spatial extent and time series. And they also have different temporal dynamics and are active at a different point in time. So if you now imagine these signals all mixing, we get our EEG MEG activity. So let's check a little bit. So this will be now a movie, which will pop up soon. So here we have measured EEG activity, and here we have activity of one component that I estimated with magic tools. And here we have the measured EEG activity. And now soon the more components will be added to the measured EEG activity. So you can see how it evolves, maybe. So so each component has different type of spatial extent, and it will contribute to several channels more than others. And you can see a complex picture arising where there's neural activity, so to say, of different frequency and different spatial extent, but there's also artifacts. And maybe the artifacts will contribute here to the C5 channel more than to others. And of course, our favorite eye blinks that we just cleaned in the pre-processing tutorial. I mean, right, you see the eye blink is here in the front, most visible, but it has also some contribution to the back, to the activity that we record at the back. So good to know. So here's also a little bit of a simulation to illustrate just the effect. So imagine you have some sources in the brain that are distributed all over the cortex. So this would be, for instance, sources, alpha sources. And you can then compute with help of these spatial patterns that we saw, the spatial topography, how the source would propagate, contribution to a single channel. Okay, so here occipital sources are colored in purple. There's one for the left hemisphere and the bright version for the right hemisphere. And you see that even for frontal channels, the contribution of stuff that is back here can be very large if the signal is strong. So this is for the eyes closed case where these contributions are the strongest. So it's a little bit of, I don't know, making people aware that this could happen. It's less shocking in other cases, I would say. But the takeaway here is that the observed spectral peak that you measure with your spectrum could also be very far from the actual electrode. So things to keep in mind. And I think this is an illustration how you could get, for instance, an effect at the top of the head if you have auditory activity. So here I simulated some sources in the auditory cortex, located in the auditory cortex. And depending how they are oriented, and some of these orientations are not really realistic, but if they are active at the same time and summate, they could also show up with most contribution at the top of the head, basically. So we will learn more about this in the source estimation lectures and hands-on. But I think it's good to be aware of these things. All right. So, yeah, we covered a little bit of ground, just a very basic flavor. Unfortunately, there's only so much you can do in 1 hour. And I hope we can build on these concepts in the tutorial. Thank you.